In this video, we will perform computations of the affine connection and curvature related tensors of a metric in specific coordinate systems using Mathematica. We will use a very simple code that is written by Leonard Parker originally, and it is provided in James Hartle's book Side. This code is very simple. It only takes as input the coordinate system names and the metric, and it computes the Christoffel connection coefficients, curvature related tensors like the Riemann tensor, the Ricci tensor, the Einstein tensor, the Weyl tensor, etc. And it also computes and displays the geodesic equations. I will assume that you know the very basic of Mathematica, like entering input in notebooks and evaluate cells, assign variables, and how matrices are represented as lists, as well as how to use functions for list manipulation. If you don't know these things, then Mathematica has an extremely rich and detailed documentation available offline if you have Mathematica installed in your computer, as well as online. If you are completely unfamiliar with Mathematica, I would recommend that you start from this book here. If you don't have access to Mathematica, it's quite expensive to buy a license. You can practice anything discussed in the book on Wolfram Cloud for free. So visit the Wolfram Cloud site here, create the Wolfram ID, log in, and just start a new notebook and type what you will see in this video. So just to study and dissect the code that does the computation, let's set a goal to compute everything that we mentioned before for the Friedmann metric. It is defined in four-dimensional space-time with coordinates t, chi, theta, and phi. And the line element is given by this expression, and the metric can be put in a diagonal form as shown in this matrix here. So now start your Mathematica or start a new notebook on the Wolfram Cloud. You can find the notebook that we will create here in the courses site in the video section, and you can download it for practice. And it starts with setting the conventions. So of course you don't have to type all these things. This is just for you to read now. The metric here is entered as a matrix, as we will see, and then the inverse metric and the Christoffel symbols are computed using this convention here for the placement of the indices, and the Riemann tensor is related to the Christoffel symbols by this equation here. So it is important to check that the book that you're reading follows the same convention and that you don't have to change the placement of the indices or the overall sign of the Riemann components. Similarly, the Ricci tensor, the scalar curvature, and the Einstein tensor must be checked to see whether they abide with your conventions for metric curvature and definition of the affine connection and the Riemann curvature tensor. So all these will be computed by the program that we will write now, and this is done in the original program, but we will also write code that computes the contravariant Riemann tensor, the covariant Riemann tensor, the R-square scalar, as well as the Weyl tensor. We will also use the code from the book to compute and display the geodesic equations. So now let's start with the computation. The first thing that we have to do is to clear the symbols that we are planning to use in the computations. Of course, when you start a fresh Mathematica session, you don't have to do that, but many times we make mistake and we have to restart the computation. So all these symbols be undefined and not used by our private manipulations of the results. So coord is a list of the coordinates, metric is the metric, inverse metric is the inverse metric, affine stores the Christoffel symbols, Riemann, the components of the Riemann tensor, L Riemann, the contravariant lower in the indices Riemann tensor, U Riemann, the upper indices Riemann tensor, Ricci, the Ricci scalar, scalar, the scalar curvature, Einstein, the Einstein tensor, Weyl, the Weyl tensor. Geodesic is a list of the geodesic equations, and the rest are symbols that are used in expressions that we should not define ourselves because they are assumed to be undefined. Then it is a good practice to clear all the symbols that we will use, for example, for the names of the coordinates or the expressions that will define the metric. So symbols like r, theta, phi, t, etc., m for the mass, whatever, we want them to be clear. We might not use them all for a specific metric, but it doesn't harm to clear some definitions. So we evaluate the cell by pressing Shift-Enter. Of course, nothing is computed here to be shown. Now, the first step that we need to do in order to start the computation is to define the coordinates. So the coordinates is a list with the names of the coordinates used, and they have to be put in the order that correspond to index values 1, 2, 3, and 4. So we press Enter here, and we see the names of the coordinates. And then we have to define the dimension of the manifold and store it in a variable named n. And that n is used everywhere, so it has to be correct. So we can just enter the number or use the function length that returns the length of the list chord, which is equal, of course, to the dimension of the manifold. So we can see the results by using the print function here. So the manifold has dimension 4, and the coordinate system has coordinates with names t, chi, theta, and phi. So now let's define the metric. So the metric here has to be put as input as a list, as a matrix. So here is the expression for the Friedmann metric that we will use, and this is how we will define it. So a matrix is a list of lists. So it's a list that has members, lists whose have as members simple symbols, like the numbers here, -1, 0, etc., or expressions like a of t. Of course, you remember that Mathematica uses the square brackets to define what is meant by a function, and not only other expressions too, not just functions, but always a function is represented in this way. So functions that are predefined usually start with a name that is capitalized, and by convention the functions that we define should start with a lowercase letter. So sine and cosine are, of course, intrinsic functions of Mathematica, and here you see all the diagonal elements of the metric. So let's also pause and see a small detail here. You see how I have written a square here. So when you want to square a variable, like take x and take its square, you can do it in two ways. You can do it in as a one-dimensional input, and probably this is what you have to do if you use the Wolfram cloud. So you should write something like x carré 2 or a of t carré 2. That is the same thing, x squared a of t squared. Now we can write more legible input by actually putting the exponent as a superscript. So in order to do that, we press X, and then we press Control 6, and you see that the cursor moves in the superscript position, and then we can write 2 for the exponent. And if we want to leave the superscript position, we press Control space, and we go back to the line. So I do the same thing with a of t. I press the key A, square bracket. You see the right square bracket is typed automatically. Then the variable t. Then I exit the square brackets. Then Control 6. You see the Control 6 is where in my keyboard is the symbol of the exponent, the carré here. So it's easy to remember, at least in my keyboard. And then I press 2 for square. And then Control space moves me back to the line. So, of course, we don't have to do this. Let's delete this cell. We don't need it. So, after that, the metric is defined, and we can display it by just typing its name, Shift-Enter, and you see the output as a list of lists. So each row of this matrix is a list by itself, and all the rows together compose a matrix in Mathematica, which has no, which is a subset of what lists are in Mathematica. Now we can view something that is a list of lists that usually represent a matrix by using the function matrix form. And then the same list is typed in the output in something that we usually use to write down matrices. So this way we can check easily whether we have entered correctly the elements of the matrix. Now the next thing we have to do is to compute the inverse matrix, the inverse metric. So the inverse metric is just the inverse of this matrix. So we use the function inverse to invert the matrix metric, and then we use the function full simplify to do some simplifications. So we enter, Shift Enter, does the computation, and then by typing the name inverse metric and Shift Enter, we see the result of the inversion of the matrix. That is a non-trivial computation, of course, and we can see it in matrix form by applying the function matrix form. Now I assume that you know how to play with lists, but let me remind you how to access particular elements of the list. So that is a list of lists containing the metric components. So a specific component can be obtained by typing 2 square brackets, 1, 2. So and there we can write the 2 indices referring to the row and column of the matrix. For example, 1, 1. That is equal to -1. Or 2, 2. That is at squared. Similarly, chord is a list, and we can access the coordinates with the same notation. So the first coordinate is the time, the second coordinate is chi, and the other coordinate theta, theta and phi. So let's see how we will compute derivatives of the metric. So you see, for example, that metric 2, is a of t squared. Oops. So let's copy this input here. So one way to take the derivative is to use the function capital D that takes the derivative, and then it's a function of one or more variables. And then comma, we write the name of the variable that we want to differentiate with respect to we want to differentiate. So you see that a square is 2 times a prime, which is quite elementary. If we use chi, then the result is 0. If we use theta, the result is also 0. So, since we have to take many derivatives now with respect to different coordinates, we can use the list of the coordinates to specify which one is used for the derivative. So if we use chord 1 here as an expression will be substituted by t, and the result will be the same as if we had written t here. So look, the result is the same. So we will use this way of computing the derivatives to calculate the Christoffel symbols. So let's play a little bit more and see how we can take many derivatives. So we can use the table function to compute the derivative of the 2, 2 component of the metric with respect to chord I when chord I, and then I goes from 1 to n, so I don't have to type 1, just type 1 takes I takes value up to n. So this is a list of all the derivatives with respect to all the coordinates t, chi, theta and phi, and you see here that only the derivative with respect to t is non-trivial because a does not depend on the other variables. Now if we take a different component of the metric, let's take the 4 component of the metric and put it here. Then the expression is slightly more complicated because now the 4 component of the metric depends on t, theta and chi, but not on phi. So you see this derivative here is equal to 0. So now you can imagine how we can use table to compute all possible derivatives of the metric. We can put here j and k, and then vary also j up to n and k up to n. So you see now that we have all the combinations for the derivative of the components of the metric with respect to any of the coordinates. Of course, this is a mess, and it is not so easy to figure out which derivative of what component is in the list, but we will soon see how to sort out this. So now that we know how to compute the derivative of the metric with respect to any coordinate, let's use this knowledge to compute the affine connection. So I will use this delayed definition of the affine symbol here. I'm not so sure why it is necessary, but I keep the original code's notation and expressions. So let's see what this definition does. So first of all, in the middle, you see the computation of the Christoffel symbol. It has 1/2 and then the inverse metric multiplying the derivatives of the metric as they are entered in the formula that gives the Christoffel symbols of the Christoffel connection related to G. Now, you see this is the inverse metric. The indices I and S are put here. And then we have to take the derivative of GSJ with respect to K. So we will use what we learned here and use the function D that takes the derivative of the metric Sj, which is GSJ, with respect to the coordinate K. So that is the derivative here with respect to xk. And similarly for the other terms here, we take the derivative of the metric, the component sk, with respect to the coordinate xj. And I don't have to explain the third term. It's completely the same thing. Now, you see here that there is a dummy index which is summed over. So S is upstairs here and S is downstairs in every term here. So a sum over S is implied in this expression. And in order to compute the sum, we use the function sum. Then we have an expression that depends on an integer variable S. It's complicated, but there is S everywhere here. And then we say that the sum is for those expressions while S takes all values from 1 to n. So this will give us gamma I, j, k for specific values of the indices I, j, and k. So now we want to compute all the Christoffel symbols. So we create a table for all values of I, j, and k. Here there are derivatives involved and algebraic expressions, and we use the function full simplify to do all possible simplifications that Mathematica does so well. So we press Shift Enter to evaluate the affine, and let's see how to access the Christoffel symbols as they have been computed. In fact, they are computed right now, they have not been computed yet. So I press Shift Enter, and you see here a list of lists that has all the Christoffel symbols. The Christoffel symbols have 3 indices, so we have a list of depth 3 in the Mathematica terminology. So you see we have a list that has a number of lists, and each list like this has lists as members, and then the lists that are contained at that level have simple symbols as members. So let's try to make this output slightly more legible. So as we said, we can access the ith element of a list by using this notation with a double square brackets. So if I write affine I, in fact, let me put here, let me not show you substitutions here, let's say affine 1, you see here that we obtain gamma 1 jk. That is a matrix, because we only have two free indices, and we can use matrix form to display it as a matrix. So that is gamma 1, 1, 1, gamma 1, 1, 2, gamma 1, 1, 3, etc., etc. And you also see that the fact that the affine connection is torsion free, those matrices here, this matrix here is symmetric. And we can repeat that for all other indices, gamma 2, gamma 3, and gamma 4. So these are the Christoffel symbols for this affine connection. So if we want to see all these together, we can use the table function, make the list element that we want to access a variable I, and then ask I to be varied from 1 to n. The 1 here is implied. So here we have a list of all those matrices. So you see they're displayed as a list of matrices because I have used matrix form to display each list of lists here. And I can use table form to have each matrix printed in a separate line, like a table. So look the documentation for table form, you can write very neat tables of things to view them more easily. Okay, so these are the Christoffel symbols. So let's now to work out the problem on how to select from this list only the non-zero components, and since this information by itself will not be very useful, also compute the indices that correspond to those non-zero elements. So let's look at this function here. There is this function unsame, and this is a logical function that takes values which are either true or false. So if you put here an expression, you can compare it with whatever you put here in the second slot. So if I put here 1, 1, 2, then this will be true if this is non-zero, but 1, 1, 2 is false, is 0, so this is false. But gamma 2, 1, 2 is non-zero, so unsame Q gives us true. So then we will use the function if to figure out what to do when these affine components are 0 or non-zero. So let's remember how if works. So if you put here something that is true, okay, the symbol true is the result of any logical function, so this is true by definition. Then it returns the first expression here. Now if it is false, then it returns the second expression. So if I put here an expression that returns true, like affine 212, sorry, I should have put the full expression. Then this is true, because this is non-zero. But if I put this element, which is 0, then it returns false. Now, if I omit the expression that is returned when something is false, then null is returned. So then it returns true. Now it returns nothing, null. So let's see how we can use this to compute the elements of the Christoffel symbols that are non-zero. So we define a list, we call it list affine, which is a table of let's forget this for the moment. This is complicated. So it takes all the components of the affine connection, affine ijk. You see ijk is are taking all possible values for the table here. And if the affine connection component is non-zero, then this is entered in the list. Otherwise, you will see that nothing is entered in the list. So let's look this list. So yes, this list has the same structure as the affine connection here, has depth 3, but you see that all the elements that are 0 have been replaced by null. So let's try to do something more useful. Let's instead of just having the value of the non-zero component, let's also compute the indices that correspond to that non-zero value. So instead of just computing affine, we will compute a list, we will display a list, we will insert a list that has two elements. The second element is the non-zero component of the affine connection. The first element here looks a little bit confusing, but it's not. Is the symbol gamma, where I put as a superscript the index I. Remember, I takes values from 1 to n. And as subscripts, the indices j and k. So that will just insert the symbol gamma ijk, with ijk replaced by the numerical values that correspond to the component of the affine connection. So we will have a label of the set of indices that correspond to the non-zero components. So if I do this and this, you see that all the non-zero components now come as pairs here, where the first element of this pair is the symbol gamma and has 1 as a superscript and 2 as subscripts, and that tells us that gamma 1, 2, 2 is non-zero and has the value AA prime. And correspondingly here, for example, gamma 4, 4, 1 has the non-zero value A prime divided by A. So now to do something useful with this, for having an easy to read display, we want to get rid of all the nulls. So as a first step, we manipulate this list and flatten it out. We use the function flatten, and you see the result is to have a list of depth 1 that has all the elements of the list, which is here of depth 3, but it could have been any depth you liked, in the order that we encounter them while reading the list here. So now we have series of nulls, and then again pairs of non-zero values of the Christoffel connection and the corresponding set of indices that they correspond to. So what we want to do now is to take this simple list and remove all the nulls. So there is a function that manipulates lists this way, which is called delete cases. So we take the result that we produced in the previous cell, and delete cases will delete all the elements of the list that are null. Here you can put anything. You can put 0 or cosine theta or whatever you like. It will delete the elements that are exactly matching that expression. So you see now that the result is a list, a simple list of depth 1 that has the Christoffel symbol with its indices and its non-zero value next to it. So what we want to do now is recreate those pairs and have a list of pairs. So for that, there is another function that manipulates lists called partition. So we take the expression that we just wrote in the previous cell. So that is the same thing here. It produces this flat list, and then we partition this list in pairs. That's what this 2 means here. So if I press enter, you see that I have a list of pairs where the first element of each pair is the Christoffel symbol with the indices and the non-zero value that it takes as the second element of the pair. So that is what we wanted to do. So all we have to do is to display this in a nice way, and we use table form for this. And here we have a list of the non-zero components of the Christoffel symbols. And now we can take a pen and pencil and, I don't know, write them down and keep them in our notebooks. So table form can be used equivalently with this notation. So that will produce the same result. But if I use this notation, then I can also make the table look nicer by putting extra spaces along the elements of the table. So if I write 2, 2 here, what it does is it puts 2 spaces along every row here and 2 spaces along a column. So you see here, if I increase this number, let's say to 8, then these are moved more to the right. If I increase this number here, then there is more space between the rows of the table. So now we can use what we have learned for computing the Christoffel symbols for the computation of the Riemann tensor. So now this is the Riemann tensor. It is a slightly more complicated expression here. It involves derivatives of the Christoffel symbols and products of pairs of those. So we make a definition in the same spirit that we have used for computing the Christoffel symbols. So let's dissect this definition here. We create Riemann to be a list that contains those mathematical expressions here for all possible combinations of the indices I, j, k, and l. So we have a table for I, j, k, and l, taking all values between 1 and n. And the first term that we have to compute is this one. Has the differences of those derivatives of the Christoffel symbols. So you see we use the function d to compute the derivative with respect to the coordinate k. So here we want to compute dk gamma I lj. So we put here coord k, that is the variable with respect to which we take the derivative, and then gamma I lj is the value of the Christoffel symbol component. Now the second term is similar. Don't forget the minus sign here. So now the derivative is with respect to the other component. Here you see we have KL to be the final indices. So the first term has K in the derivative, then the other one has L. So that is called L. Then the remaining index of the last two ones is coming here. So that is the same thing as here. And J and I. So that will give us the first two terms. The other two terms are quadratic in gamma, but they also involve a summation. You see there is a dummy index that has to be summed over. So again, we use the function sum, and we use the symbol s as the dummy index for summing it from 1 to n. So you see here, we write explicitly the expressions of the Christoffel symbols. That is affine IKS, affine SLJ, affine ILS, affine SKJ. So we press enter for the evaluation, and then now I can display the result, which is of course has lots of stuff, since now we have 4 indices in the Riemann tensor. So as before, we can create a list of all the non-zero elements. So without repeating all the details as before, let's write the full expression. So again, we make a table of all the non-zero components. Well, not exactly all, because Riemann tensor is anti-symmetric with respect to the indices k and l. So you see L here is not summed from 1 to n, but from 1 to k minus 1, because we don't need to have the components that are related by this very simple anti-symmetry property of the Riemann tensor. So again, we ask whether Riemann IJKL is 0, and if it is not 0, then we write a pair, this list, The first has the indices that correspond to this non-zero value. So you see I use superscript to put I as a superscript, and then subscript to put J, K, L as subscripts. And then the value, the non-zero value that this component takes. And then, after I have created this list, I can use this way of removing all the null elements and type pairs of symbols of Riemann tensor components and their corresponding values. So this is the result. You see all the non-zero components of the Riemann tensor, non-trivial calculation. It would take you some hours to complete it correctly, but it's done in a few milliseconds on my computer. And then we can write them down and use them in any other computation that is necessary to know these components. So let's also look at the result in a different way. Riemann is a list of depth 4. So if I take, let's say, an element 1, 2, that is a list of depth 2, which is a matrix. So if I use matrix form, I can view it as a simple matrix. So I can do the same thing that I did for the Christoffel symbols and display the matrices with respect to the last two indices of the Riemann tensor by creating a table. Oops, sorry. Instead of specific values of the indices, I put here I and J. And of course, I and J take all possible values 1 through n and J through 1 through n. And you see that we obtain a list of all those matrices. Now look at each matrix here is anti-symmetric, reflecting the fact that the Riemann tensor components are anti-symmetric with respect to the exchange of the last two downstairs indices. But this is also a list of depth 2, so I can also view it in a matrix form. And I can look at the Riemann tensor here as a matrix of matrices. So you see all those diagonal matrices are 0, but each matrix here is anti-symmetric. So let's now calculate the contravariant Riemann tensor. So we want to lower the first index of the Riemann tensor using the metric. That is a very simple calculation. We will do it in a similar fashion to the ones that we have performed before. So you see there is one dummy index, the index sigma here. So I use sum to multiply the metric with the Riemann tensor, and now the dummy index here is a double I, varied from 1 to n, so I have to make this sum over all these terms here, where s is summed over. And I have 4 indices remaining, I, j, k, and l. So this is also a list of depth 4, but by doing the same thing as we have done for Riemann, if we look at the different independent components that are non-zero, they are fewer than for the Riemann tensor, because, as you know well from the class, this index is also anti-symmetric with respect to the first two indices. So R2121 has the opposite sign as R1221. So there's no need to display both of them. And how do we accomplish this? You see here that in this table we sum L from 1 to k minus 1. We don't need to sum up to k because of the antisymmetry. This will give us 0. And j is also summed from 1 to I minus 1. So we don't enter results that differ simply by a minus sign. So let's look at this tensor in a matrix of matrices form, like we did for the Riemann tensor. This is the result here. And you can also see that in that case, those matrices here differ just by a sign. So the matrix of matrices is also antisymmetric, reflecting the fact, of course, that the lower index Riemann tensor is antisymmetric with respect to its first two indices. So you see that this is true for all matrices here. Now let's calculate the contravariant Riemann tensor. Sorry, the covariant Riemann tensor. That means we have to raise those last three indices of the Riemann tensor, multiplying by the inverse metric 3 times. So in order not to repeat similar things, let's do this computation at once. So the only difference from the contravariant Riemann tensor is that now we have to sum over 3 indices, alpha, beta, and gamma here. So you see we have a sum, and the dummy indices are called here j, j, k, k, and ll, and the inverse metric once, inverse metric twice, inverse metric 3 times, and the Riemann tensor here. And you see that j, j, k, k, and ll are the dummy indices, which here I display as alpha, beta, and gamma. And I create a list U Riemann, U for upper indices to remember it easily. And the result is this. And the reason I calculated those two tensors is because I can now calculate the curvature square scalar. So this calculation is now very easy because I have all those tensors ready. So all I have to do here is to multiply L Riemann with U Riemann, L for low indices, U for up indices, and then all the indices must be summed up to all their possible values. So you see calculations that are quite long are very easily done by using this very simple program. So let's see now how to compute the Ricci tensor. So let me write down, oops. The full code. So Ricci is Riemann, where the first index and the third index are contracted, which means they're summed over. So I use the function sum. The dummy index is I, and then the two free indices are J and L. And then list Ricci will select all the non-zero elements. So you see that Ricci is a diagonal tensor, which we can also see using matrix form. Let's calculate now the scalar curvature. Now that we have Ricci, it's quite easy. All we have to do is to contract the free indices. So we have Ricci ij, and this is contracted by the inverse metric ij, and I and j are dummy indices. They have to be summed over using the function sum. And that is the final result. Now let's calculate the Einstein tensor. So the Einstein tensor is simply Ricci minus 1/2 scalar times metric. So scalar is just a number, so we just multiply it with the matrix metric. And we see that the Einstein tensor is, of course, also a diagonal matrix as expected. That is how we display it in matrix form. Now let's do a slightly more complicated calculation. Let's compute the Weyl tensor. So this is the Weyl tensor with Greek indices, and here I write it with Latin indices so that we avoid to make mistakes. In the computation. So the first term is the contravariant Riemann tensor. So that is L Riemann IJKL. The second term here has those anti-symmetrized pairs, and we can write them explicitly, which is metric Ricci minus metric Ricci minus metric Ricci plus metric Ricci, and then the ones that involve metric minus metric times the scalar curvature. Now look here that I use the condition if the dimension of the manifold is greater than 3, because as you know the Weyl tensor is identically 0 in lower dimensions. So in that case, if n in your computation is less than 4, then this will return nothing, an empty list. So here we obtain an empty list because it happens for this metric that the Weyl tensor is identically equal to 0. So all the information for the curvature of this tensor is in the Ricci tensor, and you know that in that case the Einstein equation is fully determined by what is the right hand side, which is the stress energy tensor. So, but this is not true for other metrics. Now let's see how to calculate the geodesic equation. This is the code. We create geodesic as a list, and you see here that we use the U symbols to be the components of the first derivatives of the coordinates with respect to the affine connection, the affine parameter. So that is what the second derivative is equal to of those coordinates. And then you see that I make a substitution where each U of I is substituted by the name of the coordinate. And because U is the derivative of the coordinate with respect to the affine parameter tau, I subscript it with tau. And then I make a list that has the first term of the geodesic equation, which is the second derivative of the coordinate. So you see I take the name of the coordinate, coord I, and I subscript it with the symbol tau tau, indicating the second derivative with respect to the affine parameter. Then the symbol plus, and then the result of this computation here. But I also substitute the UI's by the names of the derivatives of the coordinates. So you see that the result here is displayed in a very nice form. So this is the first geodesic equation that has the second derivative of the t coordinate, then the one that has the second derivative of the chi coordinate, the theta and phi coordinates respectively. So these are the geodesic equations here. And that completes the computation for the Friedmann metric. So let's apply what we have done for the Friedmann metric for other metrics. And let's start from a very simple example here, that of the two-dimensional sphere. So because we will be doing this computation again and again, what I have done is I have written the code in a compact form that fits in just one cell. And you can download this notebook template from the courses page, web page. So here I collected all the commands that we have seen and analyzed before for the Friedmann metric, and what you need to do in order to use this code is simply define things here. So anything else you don't have to touch, except if you need to clear some symbols that are not included here. So you see here for the two-dimensional sphere, I set the coordinate names to be theta and phi. The dimension is equal to 2, and the metric is diagonal, and the diagonal elements are 1 and sine square theta. So all I have to do now is to press Shift Enter, and at the end of the cell, all the results are printed in a neat way. So this is the output. this is the end of the code here. So the manifold has dimension 2. Theta and phi are the coordinates. That is the metric, the inverse metric. These are the non-zero Christoffel symbols, the non-zero components of the Riemann tensor. One non-zero component which is independent for the contravariant Riemann tensor, and one for the covariant. The curvature scalar squared is 4. The Ricci tensor is diagonal. 1 and sine squared theta are the non-trivial components. The curvature scalar has value equal to 2. And of course the Einstein and Weyl tensors are trivial in this case. And these are the two geodesic equations that you can solve on the sphere. So you see that now my job is very easy if I want to carry on and study different metrics. So it's a matter of seconds to compute things for the Schwarzschild metric defined here, and I'm considering here the outside of the horizon region with coordinates t, r, theta and phi. So I copy paste the cell with the code from the template, and all I have to do is to edit things between the two red lines here. So the names of the coordinates are t, r, theta and phi. The dimension is equal to n, and n is the dimension, it is equal to 4. And this is the metric here, diagonal form. And you see here that I use the symbol m for the mass, and I have to make sure that I have cleared it from previous computations. So I press Shift Enter. Manifold is 4-dimensional. Coordinates t, r, theta, phi. The metric, I check here whether I have entered the metric components correctly. Now the rest are computed correctly by Mathematica, I don't have to worry about them. The Christoffel symbols, the Riemann tensor, the contravariant Riemann tensor. Now this is the interesting part of the computation here. Gives us the scalar curvature squared here, and you see that this is equal to 48m squared divided by r to the 6. So we note two things. First, that there's nothing wrong when r is equal to 2m, reflecting the fact that space-time is not singular as we cross the horizon, but it blows up as r goes to 0, reflecting the fact that at r equal to 0 we have a true singularity of space-time. The Ricci and Einstein tensors are 0 by construction, in fact, because that is the solution of the Einstein equation in the vacuum. That is the Weyl tensor, and the 4 geodesic equations. So we can write them down here, and we can compare them to the results that are computed and shown in books like the book by Hartle. So that's it.